right at the top of this lesson, important. I need your full attention. This lesson is extra important this year because, and it means I have to go a little bit slower over it because every year in pre-A somehow there's always one lesson that gets left behind no matter what. Like I try to cover everything and one thing gets left out. One year it was redox. We did redox last year. So that did not get left behind. This last year it was intermolecular forces. And so this is actually new for everyone, but it is important. It's really important. It's going to be really important for the rest of the unit. There's a ton of questions that Cambridge loves to ask about intermolecular forces, number one. Number two, what it is it's how two molecules interact with each other in different states of matter. So this goes to the rest of this unit of study, intermolecular forces. It's an absolutely important idea. You've got to understand polarity to understand IMF, so you're going to need to pay careful attention, especially if polarity was confusing to you. And like I said, today I'm not giving you Cambridge questions because I need you to practice what we've done so far, like at an earlier intermediate level. And then next class, after next class's lesson, you'll receive Cambridge questions after Thursday. All right, here we go. Intermolecular forces. I'm going to read through the objectives and then it's going to look like a bunch of nonsense, but I'll explain what everything is as we go along once we get through the objectives. It's going to look like a bunch of nonsense when you first read it. Like when you first read science words, they always look like really weird and what the heck are they talking about? And then it gets described and explained and you're like, oh, okay, I get it. So here we go. Describe van der Waals forces as intermolecular forces is intermolecular in the first place. And I will do that as soon as we go through these. Describe types of van der Waals forces. There's instantaneous dipole-induced dipole, also called, we'll often call them dispersion forces. Underline that word dispersion. I was taught dispersion forces. It's less words, so I use it. Cambridge allows it to be used. So you'll see me use dispersion forces. However, Cambridge also uses terminology for the first type. And the second type is permanent dipole-dipole force, including hydrogen bonding. This was the one topic that I left off in pre-A that I really shouldn't have. Every year, there's always one that gets left off. And hydrogen bonding, have you heard of it before? Maybe in biology? Hydrogen bonding? It's a really important special force we'll be talking about today. And describe hydrogen bonding, what exactly that is, and go over ionic, covalent, and metallic bonding and know that they are stronger than intermolecular forces. So there's a couple things that are brand new in here. One of them is intermolecular forces and all about it, and the second is metallic bonding. We didn't go over metallic bonding. So this is actually a two-part lesson. Today's part 1, and Thursday is part 2. And so let's go ahead and get to it. What in the world is an intermolecular force? And so just to be clear, let's say you've got methanol. Yes, I know it's organic, I'm sorry. Methanol. Let's look at methanol. How is carbon bonded to hydrogen in methanol? How is carbon bonded to hydrogen? What does that line represent? A single bond. What type of bond? Is it covalent? Is it ionic? What is it? It's covalent. Every single one of these lines between two elements represents a covalent bond. A strong attraction between that carbon and that hydrogen because they are sharing electrons. So they're fused together is the way it's thought of when you have a molecule. Let's talk about something else here. In methanol, would you call it polar or non-polar? Polar. Polar. Why? There's a fact. Because of the oxygen. This is really electronegative, right? Really electronegative. I'm just going to put the number 0.5 there because that's what oxygen is. You don't need to memorize it, but it's really electronegative. And what does that mean is happening with the electron cloud for this molecule? It's converging around that oxygen, right? So we would say that this is partially negatively charged, and the other parts of that molecule on the other sides are partially positively charged. So far, are you following me? So I stated that between the atoms of a molecule are covalent bonds. Between the atoms of a molecule, I gotta see if I have any methanol. Methanol is actually quite interesting. Methanol. Between the atoms of a molecule are covalent bonds. So those are intramolecular forces. So put it equal sign intramolecular force. So intramolecular force is something that holds the molecule or the compound together. So this carbon and this hydrogen are held together by what we call an intramolecular force. So far, kind of so good. Intra. Have you heard of internet versus intranet, by the way? Anybody who's a computer savvy person? Intranet versus internet? Because those prefixes intra and inter. I've heard them before. The first place I've heard them was with computers. Does anybody know what an intranet is? Fun fact. An intranet is just like within your organization. Whereas an internet is between you and the whole entire world. So it's kind of like, yeah, inside, like closed versus open to the world. That's an internet. Now, applying what I've just mentioned here, what do you think an intramolecular force versus an intermolecular? If an intramolecular force holds a molecule together, then what could an intermolecular force be? Go ahead. Right. So the idea is, how does this methanol interact with other molecules? And so just to be clear on intermolecular forces, we're expanding. We're not just going to be looking at singular molecules anymore, but how they interact with other molecules. And so if I have methanol and I have another methanol, would another methanol also be polar? I have a question. If I have another methanol molecule, would that methanol molecule also be polar? It would. I'm gonna face it this way with the proper shape. Partial negative and partial positive. Partial positive, partial positive. So what would happen? So what would happen if I have two methanol molecules that interact with each other? Would they be attracted to each other or not? Is there a possibility? Because this has a positively charged part and this has a negatively charged part. Do positives and negatives attract?
Wait,
So if organized three-dimensionally the right way, two polar molecules can be attracted to each other. Absolutely. And so you may want to write here a little line like this. We do it as like little dots. And this is a positive side, this is negative, this is negative, this is positive. Positives and negatives attract.
Both the negative sides are the one with oxygen, right?
Right.
So they repel apart since they're both negative.
The oxygens would repel to each other, but the positive dipole would be attracted to the negative dipole. I mean, no.
So would they just join each other?
So they get attracted to each other. And so methanol molecules would be attracted to each other. So much so, methanol is a form of alcohol. Alcohol, you know, because you put on your skin, maybe. You don't drink alcohol, you're not of age. But you know because you put it on your skin, that alcohol is what state of matter? Liquid. Liquid phase means held together or spreads apart real easy. Held together, right? Liquid means they slide past each other, but it's a condensed phase. Because there's an attraction between the molecules. So this right here, and one polar molecule being attracted to another polar molecule, and it can happen with nonpolar molecules as well, although not nearly as strong, is called an intermolecular force. And so what an intermolecular force is, just to explain what it is we were talking about, is the force between molecules. Separate molecules. Not holding one molecule together, but separate molecules from each other. So forces of attraction between molecules or compounds. And if I really wanted to not say what I was talking about, between substances. And so what we're looking at is how do molecules interact with each other. And based just on this intro, can you see how polarity is going to play a part?
Part in the introduction.
Yes. Hello?
Hi, can I borrow Catalina Diaz for a second?
Sure. Okay.
Thank you.
All right, see you shortly. All right, pause here. Yes. Absolutely. And that special strong intermolecular force gives water special characteristics. Water has a lot of special properties due to its special type of connections, due to its high polarity. So it really goes back to understanding polarity. And that's where we're going to go. So make sure you just have this intro down. I haven't even really started the lesson notes yet. I just wanted to, especially because I know if you were with me 2 years ago, I did go over intermolecular forces, but you probably totally forgot. Otherwise, you may never have went over it before, so this is an introduction of what it is we're talking about. Yes?
Inter means the
Between
attraction between
different molecules.
molecules as a whole. Intra means attraction
Within.
between actual atoms and atoms.
Yes, absolutely. You have it correct. So what Hakeem said, I'm just going to repeat that. If I'm looking at the attraction between atoms in a singular molecule, how are atoms held together in a molecule? We call it intramolecular forces. Intermolecular forces is between different molecules. How do we look at different molecules and how they interact with each other? And so there's a lot in these standards that go back to that. And so it's really important that we understand what we're talking about before we get started. So this is a big word, intermolecular. It just means that we're looking at how do different molecules interact with each other. So here we go. Ready? You're gonna look at all these fancy words and what they all mean. All right, first type of intermolecular force. Pay careful attention. Turns out, and yes, I know that you are brilliant and you will correct me. So I'm gonna say almost all. Dispersion forces are the first type of intermolecular forces, and they are present between almost all atoms and molecules. So it says here all, but I know because I've been corrected in the past and I had to rephrase it. It is almost all, and I will tell you the exception. The requirement for an atom or a molecule to have dispersion forces. You may want to write in here requirement. I'll change the color so it's clear. Electrons. So right underneath here, the requirement for the first type of force we're going to talk about is electrons. So if an atom has electrons, or a molecule has electrons, it's going to be able to exhibit this type of force.
Is the electrons in the other show or just electrons?
Electrons. Just not valence electrons. If it has electrons. All right. I'm going to have to explain this a lot better, but right now, requirements. Electrons. And I know I have some diagrams here. I'm going to explain what's going on. I have a whole blank slide here, so I can do that. Let's take a look at random atoms. Pick an element of the periodic table 1 through 20. Please don't go any farther than 20 for all of our sanities. You said 5? Do you have something with boron? Boron's fine. Let's not go too high, right? Not too low, not too high. 5 is fine. Okay? Boron. All right, here we go. So let's use example. Boron. Let's go ahead and work out how the electron electrons are arranged in boron? How many electrons does boron have? All right, so 5 electrons. We learned in our last unit of study that generally speaking, 2 of those electrons should be in the first energy level, right? And 3 of them should be in the second energy level. Okay, like just simple, right? So a couple of ideas here. Some things to note. What do we know about electrons? Do they stay in the same place? So electrons move around randomly and rapidly, right? Randomly and rapidly. There's actually some fancy theorems that says we can know the position of an electron or like how fast it's going, but we can't know both at the same time. It's called the Heisenberg uncertainty principle, I believe. They move around randomly and rapidly. You can know the position or you can know the velocity. But this is the idea. So they don't just stay in the same spot. So they're going like, so we got 5 electrons going around boron's electron cloud. So far, you following me? Are they always perfectly around? Is the electron cloud always perfectly around? Or is there a chance that it could be that for a split second in time that you have 2 electrons or more electrons, just to show it like this, that are on one side of boron than the other? Is it possible that that could happen for just a split second? Not very long, just a split second. Is that possible? The answer is yes. So it is possible, and it happens, that there is a temporary shift in the electron cloud. Meaning that one side of the atom is more negative than the other. So you could write this as negative and positive. Like one side of the atom is more negative than the other. Put a dipole there, because it's partial. Terrible dipole, but. This has a fancy name. It is called, in the fanciest terms, an instantaneous dipole-induced dipole. Because typically the shift in the electron cloud is due to feeling the presence of something else that has electrons. Yes,
Ms. Willie, do you have Rosalind Sanchez?
I do.
Send her down for a moment.
Just a moment. Okay. So, it's got electrons. Electrons can move. They don't always have to be exactly nonpolar. They can shift. The electrons can shift for a second, a millisecond, over to one side of the atom or to another side of the atom. So the electron cloud can shift. This is called a temporary dipole. So this is called a temporary dipole. So what's a dipole again?
And the electrons are moving towards
One side.
of it, yeah.
And so here we would be saying if more were over here, that it'd be like that. That the arrow would be going like that, right? It's a temporary dipole because it doesn't last. And it's not supposed to, because it's something that's nonpolar. So any molecule or atom that has electrons has the ability for the electron cloud to shift temporarily. So this is called I call it a dispersion force. And Cambridge will also call it in their mark schemes IDID as of 2022. That's new terminology from the 2022 exam. So IDID forces. If you write dispersion force on a test, I've looked in the mark schemes, they do accept it. So you can use either, but you'll see IDID reference to you, so you got to know that that means the same thing. Possibly. All right. So given that I know that that now. This is for non-polar, so this is for atoms. Non-polar molecules. So atoms would have dispersion forces because they have electrons. Molecules that are nonpolar would still have dispersion forces because the electrons that they do have can move. Can polar molecules have dispersion forces? Well, do they have electrons? So they can have dispersion forces, it's just not the only type. So this is for atoms, nonpolar molecules, and polar molecules. The only requirement is, once again, that there are electrons. Do you think this force is weak or strong? Force is weak. Weak. It's the weakest of all the forces that exist because it's temporary. So it's a super weak force, and non-polar molecules and atoms that generally tend to be gases will only have dispersion forces as their only type of force. What do you think would affect dispersion forces? Like, what would give an atom or a molecule a stronger dispersion force? So what do you think affects? What affects how strong?
The difference in electronegativity.
Go ahead. Amount of electrons. Amount of electrons. The more electrons that can move. So you should write that down because there's a ton of questions that ask you to compare elements of the periodic table and why this atom will have a higher dispersion force than that atom. And one of the main effects is the amount of electrons. The more electrons that can shift around, the more electrons that can move around. So when you're looking at dispersion forces, the main comparison you should look at is amount of electrons. All right, that was type number 1, which is I would say one of the most complicated types to explain, actually. The other types will hopefully make more sense. Write this down, have this down, we're going to go on to the next one. And that's why you saw I left the empty slide here, so that I could explain what's going on. So, in the beginning, when I drew methanol, did that have dispersion force? Or the instantaneous dipole induced dipole? Yes, why? It has electrons. So the only requirement for a molecule to exhibit that force is to have electrons. Now, there's other forces of attraction that are stronger than dispersion forces. So atoms or molecules may have multiple types. And that makes it a little bit confusing, which is why we're going to go over each type, what the requirement is, and then what's the strongest intermolecular force for a specific type of atom or molecule. Yes. So as long as there's electrons can move. And so what this means, ID, is that there must be something nearby that's affecting the electron cloud to move it to the side. So that's why it's called instantaneous dipole, induced dipole. Induced means it's being caused by something. So hold on to the name dispersion for now. We're going to go on to the next type. I already explained what this is. Weak forces between molecules. That word between is super important here. Is an intermolecular force. Now, before I move on, I wanted to point out that someone, at least one student, probably most of the students have corrected me in the past when I said that all atoms and molecules have intermolecular forces. Can you think of an exception? Is there any exception? Go ahead. They do have electrons, though. Go ahead. Hydrogen, but what type? The cation. That's the exception to dispersion force, right? Why would this not have a dispersion force? No, electron here. Literally the only thing that doesn't have an electron. But it's an important ion because that's actually acid. When we talk about acids, that's acid. So that actually is really important later on in the class. But it doesn't have dispersion forces. It does have an ionic charge though, so does it have some force of attraction with a plus one charge? Absolutely. Because it's got a fully charged, it's got a full charge, so it is going to be attracted to anything with a negative charge. Just wouldn't be dispersion. Not quantified. Alrighty, so these are actually the three types. I have explained the first one. These are listed from weakest, I'm sorry, yes? So go take a picture.
No,
This one? Oh, just a circle between molecules?
this.
Here?
Yeah.
Thank you. Ah. Thank you. You're welcome. Just to put this part. Okay. These are the three types you need to be familiar with today. The first type I've just spent the past 5 or 10 minutes going over, which is called dispersion forces, also known as ID in the Cambridge Standard. These exist between all molecules and atoms with the one exception that I pointed out. These are also called temporary dipoles. What does the word temporary mean?
Not like lasting forever, doesn't last forever.
And really, when we mean temporary, we mean like split second kind of deal, like it's here or gone. So temporary, kind of like, if you've ever heard of temporary employment, it means you don't have a permanent job. You only get to do that job until it's done, and they're like, bye-bye, we don't have to hire you anymore. That's what a temporary position. So temporary means it's not going to last very long. Not very long at all. Permanent dipole is different. So what's a permanent dipole? What is the difference between temporary and permanent? If I say I have a permanent job, what does that mean?
You're gonna work there forever.
So like that, right? Forever, right? Forever and ever. So a permanent dipole would happen how? Permanent. Well, what's a dipole? What's that?
That's when there's one positive side and one negative side.
So for a molecule to have a permanent dipole force, what would the requirement be?
One side is more electronegative than the other one.
So you may want to write here for the first one, the requirement was electrons, right? Requirement, electrons. The second one, the requirement is
Electronegativity.
well, difference in electronegativity. And we would refer to that as, for some molecule to have a positive and negative charge, we said it had to be partial positive and partial negative, it had to be polar. So you're going to want to write that down, which is why I said at the beginning of today, you have to understand polarity to understand everything that comes next. Because the requirement for you to have a permanent dipole force between two molecules is for you to have polar molecules. So we're going to have to review that, right? Polar molecules. And you need 2 of them. You need a minimum of 2. Because remember, it's the attraction between multiple molecules. Finally, hydrogen bonding is a special strong dipole. Special stronger dipole. So it still requires permanent polarity, so permanently polar molecules. However, in order for a molecule to exhibit hydrogen bonding, it has to have hydrogen connected specifically to 3 specific elements that I've mentioned in the past. In order for molecules to have the special stronger type of connection, it has to be hydrogen bonded to FON. What's special about those 3 elements?
They're most electronegative.
Right. So it gives you the biggest difference in electronegativity. So the idea is that one of the 3 most electronegative elements, this results in the largest difference in electronegativity, which means, another way of saying it, this is not Cambridge wording, this is just a me thing, is superpolar. It's like extra polar. It's superpolar, right? So the way to understand it is that it's super polar, extra polar, extra partial positive charge, extra partial negative charge. So whatever is influenced by charges, like forces of attraction. That force of attraction is going to be stronger if you have a molecule that hydrogen bonds. What do you think is the most famous hydrogen bonding molecule?
Oxygen, H2O.
Water. Water is the most famous molecule that hydrogen bonds because it's got hydrogen connected to oxygen, and it's small. Like this. Special, strong bonding capabilities. This is why water has a higher than normal boiling point. This is why water is has a high surface tension, is because of its ability to hydrogen bond. Like I said, next class I'm going to set up the water bending for you, see if you can do it, and we'll do that with water because water's so special. So after you take your test, for those of you taking nice math. Yes, next class. Give you something fun after you take your exam. Still have a lesson. We will water bend. If you can. You can't stop, won't stop, right? All right, so am I good to move on? We're good? So what are we going to have to do with this information? First of all, you're going to have to make predictions. You're going to be given a molecule, you're going to be asked what forces of attraction it has, or what intermolecular forces it has. One of the big things you're going to be asked is comparing different atoms or different molecules and ask what's affected in its intermolecular force. So we'll take a look at that and all of the properties that intermolecular force affects as we go through both today's and next class's lesson. Like I said, the main thing I want you to get down today is how to predict polarity again, and also how to predict intermolecular forces, which we'll do. So this is a chart that I picked up from the Cambridge textbook. I want you to write a line right here. Write a line right there. Notice at the top it says ionic bonding in NaCl and its bond strength. What do we think of bond strength? What does that mean? What do you think?
Like how strong the bond is.
So what is this energy measuring? It says 760 kilojoules per mole of it. What do you think that measures? How strong of what? How much energy is required to do what? Yeah, it's how much energy needs to be input to break the bond. So in order to separate sodium from chlorine, an ionic bond to separate Na plus from Cl minus requires this much energy. In order to break an oxygen to a hydrogen in an OH covalent bond requires that much energy. Hydrogen bonding, which is to separate like water molecules, requires that much energy, and then permanent dipole that, and van der Waals or dispersion is a better way, because actually these are all van der Waals. You should probably write here, these are all van der Waals. That's how Cambridge does their terminology now. You may want to correct this on here. Cross out van der Waals, write dispersion, or ID. You should put van der Waals for all three. If you look back at the objectives, Cambridge had altered a little bit the wording. Van der Waals actually describes all of these. This is a science name, actually. All the interactions between different molecules are, as an umbrella term, called van der Waals. So I would correct that, cross that out, write dispersion in its place, and then put van der Waals here for all three. What do you notice between the difference in breaking an ionic or a covalent bond versus breaking one of these new types of forces of interaction we're talking about? What's the difference? Go ahead, Ben.
Ionic and covalent bonds require way more energy.
A lot. You don't have to get specific with numbers. Just a lot more energy. So it requires a lot more energy to break a molecule apart or to break a compound apart than to break molecules or compounds up from each other. you I try to give you visuals to help you reason what you could compare this to, not to freak you out, but I'm gonna say it anyways because I've been saying it for 10 years as I've been teaching it. So get ready for it. The way to think about it, if I have hydrogen bonding or permanent dipole bonding or dispersion, separate molecules, right? So you can think about it like separate people. Let's say that you're holding hands with a person, right? And someone's trying to separate the two. Will it take them a lot of energy to do so? Possibly. Depends on how close you are to that friend. They're more like an electron to you. Goodbye. The differences here, hydrogen bonding, close friends, dispersion. You can separate from me pretty easily, I don't think. So far, you have the idea of what I'm trying to say here. All right, so here's the difference. I'm going to say, I'll get your question right after this, but wait for it. So the difference is, in an intramolecular force, now imagine, and I'll use myself as an example, would it take more or less energy to rip my arm off? I told you, it'll stick with you, than to separate you from a friend when you're handshaking. Which one would take more energy? Breaking a person apart or breaking two people apart from each other? So now think of that like molecules. It takes a lot more energy to break a molecule apart that exists the way it is than to break two molecules up from each other, if that makes sense. Because the forces of attraction between are much weaker than the force of attraction that holds together. I know I've used this again for like 10 years. It sticks. It's gross, but it sticks. You won't forget it. All right, you had a question. Like I told you. Here, van der Waals. All three of these are considered van der Waals. If you look back at the Cambridge objective, it says to use van der Waals as an umbrella term for all intermolecular forces. So I wanted to point out that change in terminology. It says it right here. Describe van der Waals forces as the intermolecular forces between molecular entities other than ionic and covalent bonding. So that means everything else. You can think of it as a van der Waals umbrella. Here. Van der Waals. You may want to write this. This is the new way Cambridge wants you to understand van der Waals umbrella. Under the van der Waals force umbrella, we have three different types. Those types are called, let's do raindrops. Yeah, it's the objective slide. ID. Dispersion forces, right? Another big raindrop would be EDPD, which is permanent dipole force. And then the last raindrop would be
H bonding.
H bonds. All of these, Cambridge now wants us to know, fall under the umbrella of van der Waals forces, which basically means forces of attraction between molecules. So all I did here was make a little umbrella, and then the three different types of forces you have to know fall under that umbrella, is a way to understand it. I'll pause to give you time if you want to write that down. Good so far? No? Need time? No worries. Instead of using the word molecular entities, what can we use instead? That's like such a molecular entity. What can we use instead of that? Too specific. What can we use instead of molecular entities? I would use substance. Remember the chemist word for stuff? Whenever we don't want to exactly define what we're talking about, we say the word substance or species. Substance or species are allowed. All right, move back. So, there are two ways to affect dispersion forces. The one I've already talked about, increasing the number of electrons in the molecule. The more electrons you have, the greater the dispersion force will be. So if you are comparing two molecules that both have dispersion forces, you can look at the number of electrons, or you can look at something called about this yet, but it should be brought up. This means that if you have this versus that, which one do you think will have the higher amount of dispersion forces? The one on the left or the one on the right?
Right.
Higher. Okay. And so you can think of every, or higher ID, I guess. Because there's more carbons that are connecting. Each of these carbons are viewed as a contact. So anytime one part of the molecule can interact with another part of another molecule, we call that a contact point. So basically, the larger the molecule, the more spread out it is, the more contact points it has, the higher the dispersion forces. You won't really see much about that in this unit, as we haven't really gotten to full organic chemistry yet, but it will be brought back up when we get to unit 4, which is the one for organic chemistry. So the main one we're going to be comparing here is the increasing number of electrons in each atom or molecule. That's the main thing we're going to be looking at for dispersion forces at this point. So you should have both of them. Next type of intermolecular force, permanent dipole-dipole. This is what it looks like. What is this molecule here? HOH. That's water. Agree? This right here is HCl. That's actually hydrochloric acid. That's some water interacting with some hydrochloric acid. And if you recall, acid always dissolves in water. When you see acid, if you've ever seen acid, you will next month if you haven't, because one of our first labs will definitely deal with acid. Whenever you have acid in water, what is the look of the solution? Does anybody remember? Colorless, right? You don't see the acid. You just see what looks like it's just water. So you don't put your finger in it. You don't put your finger in it to test it, right? If you see acid in the front, you don't put your finger in it. You don't put it on your face. Do not do a finger test in this class. Do not do it. If it says acid, don't touch it. No burning yourself. No chemical burn.
Badly.
But how is it appearing? It appears as if it looks like it's just pure water, but it's not. Hydrochloric acid is attracted to water. This is showing the attraction. Water's polar, so there's a negative end and a positive end. This acid is also polar. Hydrogen being the positive end and chlorine being the negative end. So the negative end of one molecule is attracted to the positive end of the and we call this attraction a PD force. Why? So this falls under PD. Why? Because both molecules are polar, which means both of them have a permanent dipole, which means this is a permanent attraction between the acid and the water. It's not temporary, it's permanent. Now, the way that we show intermolecular forces, so showing intermolecular forces in a diagram you always write a dashed line. So I'm writing it here what you write. This right there means that it's an intermolecular force, not an intramolecular force. So I will check if you have a dashed line or if you have a straight line. If I read a straight line, like if you made this, if you had the same thing and you did this, I will be like, no, stop. Why would I say no, stop? I'd be like, no, totally wrong, no marks. And every Cambridge examiner would be like 0 marks here. Absolutely 0. Why is this like totally wrong? This This says it's a covalent bond. If I do a straight line between the two atoms, I'm saying they're permanently covalently bonded together. That this is HOHClH. That H is in the between two other elements like that. It's not like that. If a dashed line tells me that these two are attracted to each other, they're getting close to each other, but they're not chemically bonded to each other in a covalent bond. So be careful with the terminology. You use the dashed line to show intermolecular forces, whereas you do a single line to show if it's a covalent bond. So be careful. That's totally wrong. Like what I wrote there, absolutely wrong. But something I've seen students write on the Unit 2 type test. Don't do it. Don't be that person. Do it. Am I good to move on? I like to show you what I've seen before just to point out, hey, I've seen this is wrong. The last type of intermolecular force is actually, can be confusing because it's actually also a permanent dipole. Hydrogen bonding is a special, stronger permanent dipole. And to be clear here, you have to have hydrogen connected to oxygen, fluorine, or nitrogen. So a molecule like water will be capable of hydrogen bonding. What would be a molecule of hydrogen and fluorine? Literally just HF, right? Because F can only make one connection. So that's capable of hydrogen bonding. Is this capable of hydrogen bonding?
Yes. Oh no.
Baby.
Yes! That's capable of hydrogen bonding. What about not to stress you out. What about ammonium?
Yes.
So this is yes. This is yes. This is yes. This is why not? Go ahead. Doesn't have a lone pair of electrons. So it's not polar. Not polar can't be a strong permanent dipole. It's not a permanent dipole at all, right? It's completely symmetrical. Part 1 of my explanation. Part 2, ammonium has what type of charge here? That means it's part of it's an ion, which means it would be attracted not by covalent bond, but by ionic bond to other particles. Does that kind of make sense?
Yeah.
So not that, but yes that, yes that, yes that. Well, okay, what about this one? What about that? Yes or no?
Yes.
Hydrogen bonding. Yes. Right here. That's hydrogen connected to fluorine, oxygen, and nitrogen. Oh, so is this whole topic going to go into organic chemistry as well? I told you, it's going to be like a third of the exam is organic chemistry. So we have to, it's like the elephant in the room right now. But we have to at least mention it here and there before we get to the official discussion. Yes. So you just need to know that you have one molecule that has hydrogen covalently bonded to F or N, and then another molecule that has F or N with available lone pair of electrons for that hydrogen bond to take place. So let's take a look. Question on the board. So it's finally to a few questions for us to look at. This question asks us to determine the strongest intermolecular force. So I actually want to write down strongest versus all. Go ahead and write that. in the past, so I want to be sure to be clear on my explanation here. Strongest versus all. The question says strongest, but I realized when I've given this type of question in the past that my students get confused, and I don't want you to be confused. So, right, strongest versus all. Strongest means what's the strongest intermolecular force that's present. All means what are all the intermolecular forces that could be present based on the requirements. So look at HF and H2O. HF, what do we think about that? Is that polar or non-polar? Totally polar, right? Polar. Does it have electrons?
Yes.
So electrons, yes. Does it have the requirement for hydrogen bonding?
No.
Hydrogen connected to FO or N. So far, so good? All right, what about water? Isn't all the same things true for water?
Yes.
I'm just showing like the actual dipoles here. You're not being asked to do that here, but you will be asked in another type of question to show what's going on. So this is hydrogen fluoride. This is water, another acid in water. So would these two be attracted to each other?
Yes.
Absolutely, by a permanent dipole, but the strongest type is actually called hydrogen bonding. So the strongest type is called hydrogen bonding. But what are all the types of intermolecular forces that are present within the interaction between these two molecules? Is there dispersion forces, or what we would call IgID?
Yes.
As long as they have electrons, the answer is yes. So dispersion, yes. Is there a permanent dipole-dipole? Just permanent dipole-dipole from them being polar?
Yes.
Yes. PD. So it's ID for their new fancy terminology 2022, and PD. But I remembered as dispersion and permanent dipole because that's what I was taught. Still allowed. And then also hydrogen bonding. The reason I'm bringing this up, it was on the 2021 test, I believe, that they asked for some interaction like this, and they asked for all the types of intermolecular forces present. And most of the time when the students would answer, they would just answer the strongest because that's how we've done it in class. But all types are present here, just the strongest one's hydrogen bonding. So if the strongest one is hydrogen bonding, that means everything else is present. If the strongest one is dispersion, what does that mean? Is anything else present?
No.
It's just dispersion, right? So let's take a look at F2 on that note. F2. This is F2. Polar or non-polar? Is it polar? If you have your numbers, just use it as a crutch. 4.0 and 4.0, what's the difference between those two? 0. This is the definition of completely non-polar, agree? So it cannot have dipole. Cannot have dipole. Can it have hydrogen bonds?
No.
It doesn't have hydrogen. If it doesn't have hydrogen, please don't say it does hydrogen bonds. That's silly. It has to have hydrogen to have the ability to hydrogen bond. Okay, what about dispersion? Can it do dispersion? So does it have electrons? Well, it does have electrons, so electrons, yes, but everything else is no. And so our strongest force is dispersion. And all of our forces are also dispersion. You see what I'm trying to get at now? If dispersion is the strongest, that's all it has. If hydrogen bonding is the strongest, it has everything. And so that's the order from weakest to strongest. Dispersion, then permanent dipole, then hydrogen bonding. Those are the 3 intermolecular forces that I need you to hold on to this lesson today. I have a few more for us to work out together, and then I have 2 that are your turn for a check-in before we move forward. I know for those of you who like to move ahead of me, you can start working on those, but we do have a couple more to do. What about this one? Strongest versus all, NCl3. NCl3, what do we think? Should we draw the Lewis structure? it's always advised to draw out the Lewis structure. So, because it tells you if there's a lone pair of legs. You may be able to do it in your head, but don't trust yourself. Boom, boom, boom. What do we see here? What's the Lewis structure telling us? Polar. Once I know it's polar, what's its so does it have electrons?
Yes.
Okay. That should pretty much always. We said it's polar, right? Does it have hydrogen connected to fluorine, oxygen, or nitrogen? Yes? So what does that mean our strongest force is? But all of our forces would be dispersion and just to make that distinction clear. If it has permanent dipole, it also always has dispersion. Everything has dispersion forces, except for H+. Ready for the next one? Or next two? Well, actually, it says your turn. It's your turn. A, B, C, D. There's 4 of you to try. NH3, BH3, PCl3, and H2. I'm going to give you 5 minutes to work these out. When you have it, raise your hand, and this will be your sign-off. By the way, I'm getting an official stamp coming in the mail, so I'll just be stamping instead of having to sign. Either late this week or early next week. So that it'll say, checked by Miss Lee. I bought it on Etsy. I don't know if you all ever bought it. It'll make my life easier than checking your notes. I used to have a stamp back in the day. When I switched schools, like it was no longer relevant because it had the school's name on it. So like, I just got rid of it. Like goodbye. So the strongest is actually hydrogen is strongest. So the strongest is the hydrogen. Just the strongest. It's asking in this question for just the strongest. You don't have to put all of them, just put the strongest one. When you have all 4 of them for me to check, raise your hand so I can check them all. Bueno. Bueno. Bueno, bueno. You got this. On what I consider to be a hard lesson.
When it's non
Or an important lesson.
when it's non-polar, it would be dispersion force. When it's non-polar,
Forces
non
when it is polar,
permanent bonding, and there's if hydrogen bonding, this is hydrogen bonding to fluorine, oxygen, or nitrogen.
Fluorine, oxygen, nitrogen. So the red ones,
Yes.
that is fluorine with hydrogen.
Yes. Are called hydrogen bonds.
So this one would be
Permanent dipole.
I think so.
Wait, is that polar? Yes, it is, right?
It's nearly in the check.
But it would be
Like the whole
What do you mean? A?
Are you just learning about refrigeration?
How it says it.
Today.
Feelings that, especially companies like this, they need to only nice code. I only like nice. I get my paper from that code.
I get the cans and
I
I
guess
just
you're right.
No,
literally the whole
Okay. You just decided to put IP. That's what you're about. I wasn't trying to work ahead. I was just like, you going to
But you need it for biology. It's literally the biomolecules are organic peptides.
I did one thing, then I got, I think it was dispersion, and then I got permanent cycle, and dispersion.
Oh yeah.
Dude, we're talking about with themselves, right?
You are the ID.
Yeah, because it's faster.
Well, wait, what is
It's more.
what is B? But even before like
No.
It has ions.
I was there.
That's the
You guys
only
were-
thing I know about that.
It's H3.
This one,
Three.
non-polar. This one would be non-polar because look at the electronegative heat
Minus
value.
nine.
What do you mean non-solar?
This one would be non-polar.
That is what it is.
Oh, because it has no-
So it's
Right, because the shape is not this.
Strongest and then this is not going to be much because there's no
Yeah.
going on.
non-polar. So then that would be dispersion.
It has to
So
be
when it's non-polar, it has to be dispersion.
That's fine. If it doesn't have those pairs, it's not.
So you also have to watch out for the shape.
It does.
You know, I just wanted to clarify the color thing for me, so I pretty much got everything except the shapes. The shapes,
It's a very weak
shapes are
attraction
hard because you have to memorize.
because there's only 2 electrons. What is
Yeah, the shapes, the three
It's very
It's
So you don't memorize.
or dispersion. All right, who else raise your hand so I can check before we move on? This is not going to boron only has
No, but I
But
don't
it
read
looks
it.
bad. It looks bad because I wrote with a big sharp and all the letters got split.
All right, who else am I checking? Raise your hand as I come around so I can check y'all. Yeah, and neither of those is in there anyway.
I made them using vocabulary. All right, raise your hand if you still need me to check. I'm still coming around to help check. You've got another couple minutes before we continue to finish the lesson. Still working on it? Oh, it's your turn. Now it's good. Vet? Alright, over here, I'm checking. And valence electrons? No. It almost has to go.
All right, so we're gonna go ahead and continue at this time. If you did not get my signature, you can get it at the end of class. If you did not get my signature, you can get it at the end of class. So here we go. We still have a couple things to cover, some practice questions to go over. What does Cambridge ask? So let's go ahead and do that. Now that we've went through the initial ideas and I've checked that you have the idea, let's get to what we need to do. First thing, take close attention because this is a paper 2 style question. This doesn't come directly off of paper 2, but this is a paper 2 style question. Meaning that there are many past paper 2s that I've seen that test this specific standard in this specific way, and it is always worth 3 points. I'm going to tell you where the 3 points are at. So one of the things you got to remember when you're getting to the end of this year, we're not obviously close to exam time, but it goes by.
As you start to approach exam time, one of the things you've got to keep in mind is you're trying to earn as many points, which are marks. You want to earn as many marks as possible. You don't have to get a perfect score, but the goal is to earn as many marks as possible as you're going along. So knowing where the marks are at is really important. And so take a look here. It says draw a diagram. And so the first thing I want you to underline is diagram. This is actually going to go back to the very first thing I showed you today when I drew methanol. They want you to write how the two molecules interact with each other. So when they say show hydrogen bonding is a type of intermolecular force. In order to show how the molecules interact with each other, you're going to need to use dashes. And so it says between the following molecules, a molecule of ammonia with a molecule of water. So let's see where the marks are at. And I'm going to write them on the side. The first mark is correct Lewis structures. So I know some of you have already actually started to try this and you've gotten some of the marks. Correct Lewis structures. If you can provide the correct Lewis structure for ammonia and the correct Lewis structure for water in this scenario, that's going to be worth a mark. So again, the word ammonia is used. So does that mean I have to memorize that chemical formula? Yeah. For this next unit test. So it's NH3. So this is one I've seen so many times, like I could just get it from memory, but it's NH3. How many valence electrons does nitrogen have? Nitrogen, valence. 5. 1, 2, 3, 4, 5. 1 for each hydrogen?
Yeah.
Ammonia. I don't have a mark yet because I also have to get water. So I'm going to go ahead. I'm going to face it a certain way. What do you think I'm doing this? By the way, if I'm asked to draw a diagram, am I allowed to use it?
Yes.
So if I don't originally face my molecules the same way or the right way where they need to interact with each other, you can erase it and move them around because molecules. All right, so I faced mine the way I want to face them to each other. I've got one mark. The second mark is dipoles. So if you include the dipoles correctly, meaning that your most electronegative element gets the negative charge and your least electronegative element gets the positive charge, then you're on the right track. So this is partial negative and this is partial positive. And over here, this is partial and this is partial. So dipoles. By the way, something I'm going to point out because I've looked at a lot of mark schemes. Typically, they just need you to have a set of dipoles correct. Like the dipoles that you're showing interacting, that you have those done correctly. You don't have to write every single dipole that's in the molecule, but usually they'll be like, if they did these 3 or these 3, they'll give you the mark for that, for the dipoles. So I wrote all the possible dipoles, but really it's only the interaction that you need for the mark. That's part 2. What do you think mark 3 is? The dash or dotted. You can do either. Dash or dotted line. And it has to be between the partially positively charged part of one molecule and the partially negatively charged part of another molecule. So it would look like, and I'll use a different color, it would look like this. I would do it like this with dashes so you don't get it mixed up with electrons. Just make sure that what you do is clear for Cambridge to interpret. Yes. But you still have them facing in the right way. So yes, you would get all right. Before even learning what the 3 marks were. Impressive. Okay. For letting me know. After a certain amount of hours, it kicks me out. So I need to kick myself back in. Let me know when you're good here because I do have to, actually, let me just go ahead and get out. I'm gonna keep these. Apparently, I've been locked in here so long, they kicked me out. That happened. Thank you guys. I don't know. It might be giving out on me today. Let's see.
See, that's why I judged you as soon as you said it.
Let's see. AB
All
what?
the things that I'm editing on a daily basis. Like, all those audio. So,
You do know I'm still recording, right? Oh. I'm just saying all your conversations are. Because it's not recording here, it actually records on my computer, which is totally working fine. Just FYI.
yeah.
Alright, let me know if it's showing correctly now. Is it working? Okay. Alright, I'm gonna go ahead and continue now then. Thank you. Do let me know if it messes up on your devices, if you're using your devices.
Yeah.
Water.
No, I mean, like, it's both.
You can't connect the H to H because it's a positive connected to a positive. And that goes
So
that goes the
always
other way.
You have,
It's gotta be positive to a negative.
when it's,
Electronegative element to a not electronegative element.
hydrogen bonding. It
Yeah.
always has to be
Hydrogen
one
to
hydrogen with
fluorine,
one other
oxygen.
molecule.
Yes. All right, so we're gonna go ahead and continue. I had got logged back in. If you ever see me get kicked out, I won't notice the way that I have it up here. I won't notice when I'm teaching, so you gotta let me know. Thank you. Alrighty, we're gonna go ahead and continue. If you need to take a picture of it, let me know. I am also recording, so it'll be posted later on after school. Guess what? It's time for Cambridge questions. How does this look on paper too? This is in the year 2020. Meaning, this exam was never given, was it? This was the 2020 June exam. This was never given. This was an exam my students were supposed to take and never did. No. A little bit lucky because it was based on evidence. So we had to submit evidence for the students. Like we always, every year, we submit forecast grades. I don't know if you know what those are. Those are basically our predictions on whether you pass or not. You can guess what your forecast grade is because it's based on your quarterlies. So for this class, whatever your average of your quarterly exams are, that's what I put as your forecast grade. So it's very easy to predict. So anyways, what we had to do as teachers is we had to collect a portfolio of evidence of what grade the student was going for. Like if it was an A, a B, a C, a D, a E, or a U. And we had to submit that to Cambridge. And in the year 2020, they were very nice because that was the first year of COVID. And so they pretty much honored whatever the teachers said in terms of if the kid would pass or not. That's what they did in 2020. In 2021, it was a bit stricter. And then in 2022, they were back to regular testing. And then this last year that kids just tested in 2023 was back to regular grade thresholds. Meaning not only was it regular testing, but regular testing with the same amount of points as it was before COVID. So they're basically like all the COVID niceness that we gave is all gone. And so back to normal. All right, so this is an exam that was never given, but they published them anyways so that they had already written the exams when COVID hit. So this was a question that would have been given to my students. So let's take a look at it. Gallium and its compounds show similar properties to aluminium. Gallium reacts with excess chlorine to produce gallium trichloride. You are told at 500 degrees Celsius, gallium trichloride is a gas. Suggest the type of attraction. And so the fact that they're telling you it's similar to aluminium is what's supposed to help you out. What do we know about aluminum and chlorine? Is that covalent or ionic bonding? So you're supposed to draw the same conclusion that gallium and chlorine, also the name, gallium trichloride. For those of you who remember from pre-ACE or honors, if I see a tri, that actually tells me it's covalent. If I see mono, di, tri, tetra, that's kind of like just a key word that tells me what I'm looking at is covalently bonded, not an ionic compound. And so you've been given a couple of clues in here that it's covalent. The type of attraction means intermolecular force. So go ahead and write GaCl3. Do that Lewis structure. What does it look like? GaCl3. How many valence electrons does gallium have? So knowing that it's covalent, don't overstress yourself with it. This is it, right?
Yep.
GaCl3. Polar, non-polar. That's the question.
Non-polar.
Non-polar. That's what the practice is. Like, that's why I'm giving you a quiz as practice later on. Non-polar, right? Because there's no unshared pairs, and on every side is chlorine. If you were to draw it correctly, it would be 120 degrees apart, but we don't have to do that to get the answer. You just have to see no unshared pairs, all the elements surrounding are the same, so it's non-polar. So what is the type of attraction? First of all, between the molecules, let's answer that one first because that's where I'm going towards right now. If I have several gallium trichlorides, how do they interact with each other? Here's one of the names. Is it dispersion? Is it permanent dipole? Is it hydrogen bonding?
Dispersion.
Dispersion. So that will be worth 1 mark. Okay. What is the force of attraction that holds the gallium trichloride together? That first one. Between the atoms in the molecule. What would that be? Correct. That's the idea, yes. Go ahead. Do you see the difference between atoms in the molecule versus between different molecules? 1 mark for each of those. Pre-Ace asked me earlier, do I have to write these answers in complete sentences? What do you think the answer is? No, please don't. Just write covalent. Like, just answer the question. They said it's been so ingrained in them that they always have to write, like, every answer has to be in a complete sentence. Just answer the question. If it only necessitates 1 or 2 words, then you write 1 or 2 words. Don't make them read more. In this class, the more you write, the more you can mess yourself up, actually. Because it's not polar. So it has electrons, but it doesn't have a permanent dipole.
Oh, right, because it has a triangle.
Okay. So we got something interesting going on here. Look at this last point down here. Ga2CL6 forms out of GaCl3. Remember that guy? Or gal? Al2CL6 from last class that I told you you had to remember? How do we reaction that puts those two together. You do not have to draw it to get the answer. If I want to put two AlCl3s together, what attraction has to happen? It has a special name.
Hybridization.
Nope. I heard dipole and I heard hybridization. Neither of those. No. Okay. Yes, it's. So what's the name of the arrow? Does the arrow have a name? It's called a dative
Covalent bond.
or coordinate covalent bond. It's the arrow. Whenever you have the arrow, that's the specific bond that's putting those two together. It has a special name. And so that's an example of a higher level question where you have to apply what you know for AlCl3 for something else. That's that weird one where you made the two arrows to connect the two together from chlorine to aluminum and then from another chlorine to another aluminum. The attraction is called a dative bond. You have to memorize when you see the arrow, it's called a dative bond.
Which one's better to use, dative or co?
They use dative in the mark schemes, so you can circle that one.
The dative is just appreciate.
Either is fine when you have the arrows.
How are they attracted? This CL is attracted to this GL?
Yeah, it's like this and then like that. Well, you're missing the chlorine on the bottom. All right. So here's where we're going to be going to and where we're going to end today's lesson. Pay careful attention because this goes into next class. Next class, our focus is going to be what do intermolecular forces attract? And the answer, they attract a lot. Whether your molecule is a gas, a liquid, or a solid. If it dissolves in water or not. All of that has to do with the type of intermolecular force and whether the molecule is polar or nonpolar. Reactivity has to do with polarity. And so what you need to know for now, and this is again, like I said, going to go into next class's lesson. The stronger the intermolecular force, the higher the boiling point is for a material, and the higher the melting point is. This means requires more energy to separate. So IMF stands for intermolecular force. I want to make a point before moving on because I don't want you to make a mistake. When I attended training with the Cambridge Examiner, and I've been to a few with Cambridge Examiner, he made a point to say that they do not accept you writing this on a Cambridge exam. So they do not accept, this is not accepted as an acronym. I understand the trepidation. No, I would want to write it, and you see I've written it in my notes, but I want to make the point there. They don't accept it as an acronym. There's a reason why. When you say IMF, it could be inter or intra. And so they want you to be more specific on whether it's inter or intra. It was actually brought up by a bunch of chemistry teachers. They're like, what? Because it's typical terminology for us to use IMF. But they don't accept that acronym. Cambridge doesn't accept it. So they do accept ID, you saw it in the standard. They do accept EN for electronegativity. They just don't accept this one. So FYI. If you write IMF on a quarterly, I can't give you the mark because I will grade it like a Cambridge examiner. You have to spell it out. Yes, Justin, question? It doesn't need a period, just EN. For electronegativity? Mm-hmm. All right. So, taking a look at what's said here, and taking a look at this. This is a textbook question, but it highlights a very common paper 2 question, which means commonly asked on a quarterly exam or a unit exam as well. This is a very common style question. I want you to be familiar with it and how to answer it properly. So you're given a bunch of halogens. Anybody know what a halogen is? Like those, right? So you're told The boiling points of the halogens are the following. Fluorine is negative 188, chlorine is negative 35, bromine is positive 59, and iodine is positive 184. Make a note to yourself. They're not talking about singular atoms here. They're talking about the elements in their standard state. So when it's talking about it, it's talking about the elements in their standard state. What is the molecule for fluorine? It's not F. What is it? F2. F naturally exists as F2, not just F. Fluorine exists as Cl2. Down the whole group, all of them are diatomic. Would you agree? You're supposed to know all the halogens are diatomic. They all exist as two. So then the question is, first of all, describe the trend. Look at your command word. What does describe mean? What does describe mean? What happens? Describe what happens. What happens? They're not telling you what happens. You state what happens. As I go down the group, what's going on? Down the group, the boiling point, acceptable answers include increases or decreases. Which one would be correct?
Increases.
Increase. So you do not have to state the exact numbers, and you shouldn't. If they're asking you to draw a conclusion, they're asking you to look at the trend. The numbers are increasing. The boiling point is increasing. That means a higher temperature is needed to separate the molecules. So that's part one. That would be like with 1 mark. The second says to explain the trend. Why? 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 As I go down group 17, halogens, does the boiling point increase? This is where the money's at. This is where usually most of the marks are at. Why? What's the difference? The what? Not the best. Go ahead. Stronger dispersion forces. They all have dispersion forces, right? Because they're all nonpolar. So what affects dispersion forces? Number of electrons, right? So the trend is all of the halogens have dispersion forces, which increases down the group Y. Since there are more electrons in the elements further down the group. Since there are more electrons in the halogens down the group. Now there's still another point here that I haven't said, and you need to write it down because it's a very important part. And it ties into next class's lesson, which we have to talk about more. Well, what is a boiling point? What is boiling? Yeah, boiling point is going from a liquid to a gas. What does that mean on a molecular level? Go ahead. Sorry. Somebody's up. Or yeah, that's still out. He just left a little bit. Liquid to gas means when you have a liquid, your particles are next to each other but sliding past each other. But in the gas phase, everything's like
So is it that the attraction
Scattered.
is no longer there, or is that it's not enough because of the heat?
So if I have an increase in boiling point, what that means is it requires more energy to break apart the molecules from each other. Does that make sense? Higher boiling point means higher temperature necessary to break apart the molecules from each other. So then would it make sense that as there are more electrons and there are greater dispersion forces, this means their force of attraction is stronger? A greater force of attraction, a greater dispersion force will require more energy. Will require more energy separates the molecules. And don't worry, this is where next class's lesson and the next two lessons go. We're going to talk more about boiling, melting, all of the phase changes and how that looks on the molecular level. But this gives you an idea of how you need to formulate your answers. This type of question will be worth 3 marks. So 1 mark to say what the trend is. The second mark is to say why. The third mark is to basically state that if you have a greater force of attraction, it's going to require greater energy to separate the molecules. That's the idea. All right, we are close to done. I think we'll...
What's the why?
More electrons
Okay.
going down the roof. I think we'll stop here. Just to be clear, anything that I didn't finish, I'm going to finish next class's lesson. Now, I wanted to bring up again what your homework is. I'm about to post it. You're going to have 2 homeworks. Neither of them are Cambridge questions, but both of them are really going to be helpful, hopefully. First one is a quizzes. For those of you who know how the quizzes generally work, if it's a non-Cambridge quizzes, you get an 80% or higher within 3 attempts. I put 100% in the grade book. That's how that works. So that's going to be on polarity. The second is collisions. There's a website called Collisions. You're going to be working with intermolecular forces and, working with the forces together. It helps give a visual on what's happening with intermolecular forces. I need you to get a visual understanding of what's going on before we come back next class, so that as we go through, you have a better understanding of what's going on. So you've got a couple of homework assignments. Neither of them are Cambridge questions. I'll be giving those out next lesson. You like collisions?
Yes.
Your period loves that. They still talk about it, the ones that are in A level.
Can you go get some water?
Yeah, you got just enough time to go get some water. Just take this with you.